All right, let us begin. So today we're going to be covering section 6.2 in the textbook, also known as circular motion. Our agenda for covering section 6.2, circular motion, is to review circular motion, the basic ideas, the most important ideas. Secondly, we'll practice one problem together. Third, you'll have 3 practice problems that you can do on your own. And then fourth, we'll do another relatable practice problem that you see in your everyday life. Now, before continuing to watch the rest of this video, in order to ensure that you understand circular motion, you have all the tools instructional tools that you can use to understand the material. I encourage you to read, or at least skim through, section 6.2 in the textbook and watch the video that I posted on circular motion that I found from YouTube that I believe will be helpful for this discussion. All right, let's begin with a review of circular motion. There are 2 types of circular motion, 2 major types. One is uniform circular motion, or UCM, and the other is non-uniform circular motion. We will always be dealing with uniform circular motion, which means that our object is traversing a circle, or traveling around a circle, traversing a circle at a constant speed. Whereas non-uniform circular motion occurs at differing speeds, right? So the speed of our object that's traveling around a circle, and we have a circle here, that the amount of time it takes for that object to go from this bottom point of the circle to the top point of the circle is the same amount of time it takes for it to go from the top back to the bottom, right? So it's traveling at a constant speed. That's what we mean by uniform circular motion. What is that speed? Well, speed is the magnitude of velocity, right? Speed is the amount of velocity that an object has without regard to the direction of that velocity. So if 5 meters per second to the east, speed would be 5 meters per second. When it comes to a circle, we're concerned with, when it comes generally to speed, we're concerned with, well, what is the distance that the object travels in some period of time? In some period of time. For a circle, that has to do with the distance that we'd be traveling is the distance around the entire circle, so that would be the circumference, still divided by time. We know the circumference of a circle is 2 times pi times the radius of that circle, right? Here's the radius of our circle. We'll call that big R, okay? Divided by the amount of time that it takes to travel all the way around the circle, and we call that capital T, or period. This is period. The period, or capital T, is the amount of time it takes for an object traveling around a circle to make 1 revolution, or to travel around the circle once. So say, for example, if you're running track, and you're running in a circular track, and it takes you 15 seconds to go from the start to the end, or to go from the start point and get back to the start point after you run around that circle. If it takes 15 seconds, then your period is 15 seconds. This R here, I should make that capital R, is our radius, 2 pi r, that's our distance divided by time, so we have speed. Right, like I said, we're looking here at speed, not at velocity, or we're looking at the magnitude of velocity. At this moment in time, if we look at our circle, if we suddenly let our object, as long as it's traveling in this direction, right? That's its rotation, counterclockwise. At this moment in time, what is the direction of the object's velocity? We would say it's tangent to the circle. You can call it v sub t, if you like, or tangent. If you remember from geometry, that a tangent line to a circle touches the circle only at 1 point. So this is a line, and if we continue this line backwards, we'd see that still it only touches at 1 point, at this point right here. When we get back up to the top of the circle here, Now the object is facing the opposite direction. It's facing now to the left. This is its new velocity. Its velocity has changed because its direction has changed. When we say in physics that we have a change in velocity, that means we have some acceleration. There must be some acceleration. This acceleration is mysteriously pointing towards the center of the circle. It's always towards the center of the circle. That's why we call this acceleration centripetal acceleration, or A sub c. I'll write the word down, centripetal, which means towards the center. Centripetal just means towards the center. The proof for that our acceleration vector is pointed towards the center of the circle is in your textbook. You can get a sense of it, however, if you were to roll an object around a circle. You'd have to continually push it back towards the center of the circle to keep it in the circle. If all of a sudden you allowed it to just travel, stopped applying a force to it, then you'd see it travel in a straight line. And that's our next point here, is that our centripetal acceleration, if we have an acceleration, then we must have some net force that's causing that acceleration. That net force that's oriented towards the center of the circle for the acceleration is in the same direction as the acceleration, so it must be a centripetal force. This is very important. What we've seen is that because our object traveling around a circle, though it's traveling at a constant speed, because it's changing direction, at this moment it's to the right. When it gets to the top, it's now looking to the left. Then its velocity is changing. If its velocity is changing, then we know it's accelerating. It's accelerating towards the center constantly, so the acceleration vector is constantly changing, but it's always towards the center. If it's at this point, it's pointing towards the center. There's our A sub c vector. There's our A sub c vector. Here would be again towards the center, A sub c. That vector is always pointed towards the center. It's always trying to keep the object in the circle. The force, there is a force that's necessary to accomplish that, and that is our centripetal force. Now, your book provides a proof of how strong this centripetal force is. It is the square of the magnitude of the velocity, in other words, the speed, divided by the radius. I won't go through that proof here because I do not think it is completely beneficial for you to work through it. By all means, please take a look at it, but for now, I'll just give you what the formula is that we find. If we want to know what the centripetal acceleration is, how strong it is, then we need to find what is the speed, or the magnitude of velocity, square that speed, and divide by the radius. That is our centripetal acceleration. In other words, if our speed, or the magnitude of velocity, was 5 meters per second, and if the radius of our circle was 15 meters, then we'd say, all right, the centripetal acceleration of that object that's traveling around a circle that has a 15-meter radius and is traveling at a speed of 5 meters per second, that is its magnitude of velocity, or its speed squared, divided by its radius, 15 meters. So we get 225 meters squared over second squared, divided by 15 meters. And so we'd find that 225 divided by 15 is 15 meters per second squared, because those are our units for acceleration. That is our centripetal acceleration for the object that travels around a circle that has a radius of 15 meters and at a speed of 5 meters per second. Now, to make some sense of that value, because that's pointing towards the center, we don't really get a sense of what does that physically mean, though, because it's not as immediately understandable as linear acceleration. So we should take a look at the force that's necessary to keep that object in that circle with that acceleration. The net force, in this case the net centripetal force, is always equal to the mass by Newton's second law times the acceleration. Because this is a centripetal force, then we're looking at a centripetal acceleration, magnitude of that. So we have mass times, what is the magnitude of our centripetal acceleration? V squared over r. And so we say, very simply, that the centripetal force, or the force needed to keep an object in a circle, traveling around a circle with this radius and with this velocity, or speed, and this mass, is simply mv squared over r. mv squared over r. So now if we know the mass of this object, say the mass of that object, say the mass was 15 kilograms. 15 kilograms. Then we could say, all right, with a mass of 15 kilograms, and a centripetal acceleration of 15 meters per second, say 15 kilograms times its acceleration, 15 meters per second squared, and I find that the force is 225 newtons of force. 225 newtons of force that must be applied to that object constantly, and that force is always pointed towards the center of the circle. I've represented both of these as the magnitude of acceleration, magnitude of force, because we already know their direction. This acceleration is towards the center, hence the centripetal. This force is towards the center, hence the C for centripetal. All right, now we're going to take a look at a practice problem together. All right. So say if Mr. Newman swirled an apple, a 1.0 Newton apple, around his head, the length of the string attached to the apple, excuse me, the length of the string attached to the apple is something reasonable, something like 0.85 meters. The apple makes 1 revolution every, reasonable time, every 0.90 seconds. Okay. What is the tension in the string? Tension in the string. This is our work together problem that we'll be doing. So Mr. Newman swirls a 1.0 Newton apple around his head. The length of the string is 0.85 meters. The apple makes 1 revolution every 0.90 seconds. What is the tension in the string? Before listening to my explanation, I encourage you to try to solve this problem on your own. If we draw a picture of this circumstance, I have this object here that will make my circle for me, so we can draw it out. Oh, I messed up a little bit of it. That's all right. All right, here's our apple. Put our apple right there. There's a string attached to the apple. I'm standing in the middle, so there's Mr. Newman. Mr. Newman's standing in the center. That's me right there. Okay, and then there's a string that's attached to this apple. That string has a length of 0.85 meters. The apple has a weight, right? There's the weight, 1.0 newtons, not the mass. And it takes 0.90 seconds. So let's start identifying some quantities here, some things we know about the apple. Well, we know its weight, okay? We're told it's a 1.0 Newton apple. It's just like saying, I'm a 100-pound person, right? That 100 pounds is your weight, right? So saying we have a 1.0 Newton apple, that means the weight of the apple is 1.0 newtons. The length of the string is 0.85 meters. If we look at our picture, we see very clearly that is the radius. So our capital R is equal to 0.85 meters. And then our last quantity, or the thing we know, is that the apple makes one revolution every 0.90 seconds. The time it takes for an object to make one revolution, that's how we define the period. So capital T is equal to 0.90 seconds. What we're asked to find is the tension, the force of tension. Again, looking at our picture, we see that our apple here at any moment in time wants to travel this way, wants to travel in the straight line this way. But what's stopping it? This force applied to it through the tension. Notice that force is pointed towards the center of the circle. That is our centripetal force. In other words, we have our T tension. How strong that force is serving as our centripetal force. That is the centripetal force, tension in the string. We know how to quantify this centripetal force. If that's the force that's keeping our object, our apple, in the circle, we know that any centripetal force has to be equal to mv squared over r. mv squared over r. We don't have the velocity, we do have the radius, and we don't have the mass. So we're going to have to do some work here. How are we going to find the mass? Right? Well, we know mass. We need to go from weight into mass. Right? We have the weight. We need to find the mass. Well, I know our relationship between those quantities is that weight equals mass times gravity. Right? So if we divide here by gravity on both sides, we see that we can find what the mass is. We just need to take the weight of our object, which is 1.0 newtons, and divide by 9.8 meters per second squared, or 9.8 newtons per kilogram. So 1 divided by 9.8 is 0.10. 0.10 kilograms. There's our mass, so we now have our mass. Our next step is we need to find what our velocity is, or our speed, rather. Okay. To find our speed, we need to use our equation of 2 pi, distance, the circumference, divided by the period. We know the radius, and we know the period. So we can calculate what our speed is. 2 times our 2 times pi times our radius of 0.85 0.85, and then divided by our period, which is 0.90. And we get a velocity, or speed, of 5.9 meters per second. I'm going to check that math one more time to make sure I did that properly. So we have 2 times pi, or 3.1415926, times our radius of 0.85, and then divided by 0.9, and we get, okay, confirmed my number. Good. So now we have the velocity, now we have the mass, and we know the radius. We can find what the centripetal force is. We just need to take our mass, 0.10 kilograms, times the square of our velocity, 5.9 meters per second, and then square that value, and divide by our radius, 0.85 meters. This is our centripetal force, mv squared over r, 0.10 times 5.9 squared and our value is 4.1 newtons. This is our centripetal force. This is the force that's necessary to keep our apple in the circle. With a force of 4.1 newtons, our apple here can continue to travel around a circle with a radius of 0.85 meters with a weight of 1.0 newtons. We know the direction of that force. That force is always towards the center. And that's what we see. That's the force along the string. That's the force towards the center. That is the magnitude of the tension in the string. All right, for part 3, getting towards the end of our lecture here. For part 3, you will do practice problems 12, 14, and 15 on page 162. Page 162. Before proceeding to part 4, I urge you to complete these practice problems. I'll give you the answers here. I encourage you not to look at the answers until after you attempt to solve them. So by all means, please pause this video now before I give you the answers to these problems. All right, we will now proceed to the last part of our video, and that is a hopefully relatable example. You can see what my writing surface is here, organic chemistry. All right, we'll continue with our last example, and that example is one that hopefully you're familiar with, and that would be if you've ever driven in a roundabout. So we'll have one of our students. Let's see, which student shall we choose for B-Day? We'll have Jack, right? Jack drives around a roundabout. A roundabout. The roundabout has a radius. Let's see, a reasonable radius would be something like 12 meters. Of 12 meters. A smaller roundabout, relatively small, reasonable though. Of 12 meters. The coefficient of friction, that is between his tires and the road, static friction, is 0.95. And the mass of the car is 1,000. We'll say 1.00 times 10 to the 3 kilograms. Also a reasonable estimate. What is the maximum speed he can travel around this roundabout? Around this roundabout. Before spinning out of control. So I could draw a circle for us again. Again, we just have a simple circumstance of circular motion. We have Jack traveling around a circle. We know here the radius of the circle. Okay, so we say, all right, well, the radius of this circle is 12 meters. We know the coefficient of friction, static friction, so we'll say mu sub s. There's our coefficient of static friction, 0.95. We know the mass of the car, okay, 1.00 times 10 to the 3rd kilograms. And what we're trying to find is the speed, which would be the magnitude of the velocity. This is what we don't know. How fast can he really travel? All right, I will make a circle for us again. That should help. All right, circle's a little better than last time. All right, here's Jack in his car. There's the car. Traveling around the roundabout this way, we have here our radius. There's our radius of 12 meters. And that car has a mass of 1.00 times 10 to the third kilograms. Remember, his car wants to go this way. His car wants to travel in a straight line by Newton's first law. What keeps him in the circle? That would be a centripetal force that's acting on him. Here's a centripetal force, some net centripetal force. In our case, or in Jack's case, that would be the force between his tires and the road. All right, we know that is the static frictional force. All right, so let's take a look. What do we mean by static frictional force? You mean F magnitude max, right? Our static frictional force is always defined by our static frictional coefficient and the normal force. Since this is a horizontal surface, we know that that normal force is equal to the weight, right? So I can substitute in weight. Normal force is equal to weight. And we know that weight is equal to mass times gravity. Right? We were able to do all of this because we know that normal force is equal to weight on a horizontal surface, and that weight is equal to mass times gravity. So all we did was slowly substitute down until we get the coefficient of static friction times mass times gravity. That is our static friction between the wheels and the road that keeps Jack in the circle. That is the centripetal force that's keeping Jack in the circle. So we have that static frictional force, which now we know is mu times mg. That is the centripetal force. We know the centripetal force, or rather, I'll now substitute this over. We just found that our static frictional force, the maximum value that it can take, is mu of s times mg. So mu of s times mg is equal to the magnitude of the centripetal force, which must be mass times velocity squared divided by r. Mass times speed squared divided by r. We can see that common to both sides of this equation is the mass. So it doesn't matter what the mass of the car is. All that matters is the static frictional coefficient, gravity, the speed, and r. Remember, we're trying to find the speed at which he can travel, the maximum speed. This is the maximum force that is applied to him. So we solve this equation by multiplying both sides by r. So we get mu sub s times g times r equals the speed squared. In order to get speed by, right now we have speed squared, we just need speed. We need to take the square root of both sides. Mu of s times g times r. And now we have found the maximum velocity at which Jack can travel around this roundabout without slipping and traveling in a straight line. Our mu sub s was 0.95. Our gravitational force was gravitational field constant, 9.8, and then times our radius of 12 meters. That gives us a value of 111. Now, I actually don't have a square root function on my phone that I'm using as a calculator. Right, here's my phone that I'm using as a calculator, my flip phone. So I know that the square, or that inside of this value, I have something like 111. Okay? I know that 10 squared is 100, and 11 squared is 121. So it's about in between those two values. So it's something like 10.5 meters per second. Right? That's a little bit of my approximation. Of course, your calculator will give you a more precise answer, but my approximation, using just a little bit of common sense, is that the square root of 111.9, I think it was, is something like 10.5, and that's why I put an approximate symbol. So at about 10.5 meters per second, at that moment, Jack's tires will no longer be able to support a sufficient force to keep him in the circle, and he'll spin out and leave this roundabout. Here's our entire problem again. Give you a quick look at it. All right. Thank you all.